Well, good morning, everybody, and thank you very much for inviting me to talk today. If you belong to one of the large helicopter OEMs like Leonardo or Airbus or Sikorsky, I suspect this talk's going to be a little bit like looking in a mirror. And the reason is that if you make helicopters, critical parts management becomes a way of life. It is absolutely central to every step along the way of the process. So, what are critical parts? If we look at the definition from CS29, it says a critical part is a part, the failure of which would have a catastrophic effect on the rotorcraft and for which critical characteristics have been identified which must be controlled. So we have two aspects here. We have the fact that it has a catastrophic effect and critical characteristics. So what do we mean by catastrophic? A catastrophic is defined, funnily enough, in CS25, 1309, as a failure condition which would result in multiple fatalities, usually with the loss of the aeroplane, or in this case, the helicopter, the aircraft. So, what's so special about critical parts? I'm going to talk for a moment about transport aeroplanes as a comparison. Large transport aeroplanes, they certainly have critical failure modes, but it's very rare to have a single point failure with no redundancy, because usually you can design redundancy into the system. The one example we could think of where you physically can't have redundancy is the screw jack on the tailplane to adjust the pitch for trim. You can only have one, otherwise they'd fight each other. And as we sadly saw with the example of the MD-83 in Alaska some years ago, a failure of that, of course, is catastrophic. Now, with helicopters, it's different. It's the presence of so many non-redundant parts with catastrophic or hazardous failure modes all in series that makes critical parts so important to helicopter safety. Just look at that picture there. Pretty much every single part you see there, the failure of that would cause the loss of the aircraft. So, how do we determine which parts are critical parts? And I can tell you, go back to the beginning of my career, I can tell you the way that it was done is the greybeards would sit around the table with a drawing and they'd look at it and they'd say, oh, that's a vital part and that's a vital part, and they'd make a list. Well, that's not good enough. We have a much more systematic way of doing it these days. And the process is you start with a functional hazard assessment, where you look at the system, the subsystem, and you say, what are its functions? What does it do? And you list all those functions. And then you consider, well, what happens if it fails to do those functions, or if they're done incorrectly at the wrong time? You also look at, where is this subsystem? Is there anything in the zone which it could affect, which could have a catastrophic outcome, or you assess the criticality of the outcome. And out of that, you rate the criticality of the failure mode as catastrophic, hazardous, major, minor, or no safety effect. And so for each possible failure mode of the subsystem, be it something like a gearbox, a rotor, you categorize the failure mode. We then do something called a FMECA, failure mode effects and criticality analysis, where you look at every part in the subsystem, and I do mean every part, not just the major parts. You even sweep up all of the fasteners, etc., and consider all of those and think, what happens if they fail? Don't tell me they can't fail. Don't tell me they're so strong they'll never fail. Supposing it's made out of the wrong material or it's not heat treated correctly, what happens if it fails? And then you relate that failure to the failure modes that you've identified in the FHA, and so if it's a catastrophic failure mode, that then becomes a critical part. I haven't got time to go through these, but just very quickly, I'll just click on the hyperlink. Oh, up it comes. And that's a functional hazard assessment. I say that sometimes the format can vary a little bit, but basically you're looking at the function, the potential effect on zonal systems, the worst case failure. You're always looking at the worst case. In this case, I'm saying it's catastrophic. And the mitigating arguments, pretty much none. It's all only the critical parts plan. And so the overall mitigated failure criticality here was catastrophic, in this case for a rotor drive shaft. That's an example there. And the FMECA, again, formats can vary, but basically for the part, we're looking at the loss of drive here. We consider different flight phases, primary effect, overall functional effect, any mitigations. We look at the probability of failure that we would allow for this kind of failure and the criticality that it relates to. As I say, formats can vary, but basically that's the process that you're going through. So, having done this, we can now grade the parts. And if you look on the left-hand side, we see catastrophic, hazardous, major, minor, and I could say no safety effect. And typically, in the civil world, we always grade catastrophic failures as critical parts. Most OEMs also consider hazardous failures as also being worthy of being a critical part. They don't have to. The requirement is catastrophic failures, but we often do. Most OEMs introduce an intermediate grade called something like sensitive or significant, and this pretty much maps onto major. And then anything that's minor or no safety effect, well, that's a basic part. The terminology may vary from OEM to OEM, but one way or another, they categorize the parts. And why are we doing that? Well, the answer is because you can't give maximum attention to everything. You have to be able to focus on the bits that really matter. And that's why we grade the parts. On this table, I've also shown the equivalents in the UK military DEF standard 00970. We talk about vital parts and grade A identifiable. They roughly map on as shown there. In America, I believe you call them flight safety parts, but we're talking about the same process. What about assemblies? Now, assemblies can be a little bit odd in that it's perfectly possible to have an assembly which contains critical parts but which is not itself critical. Now that seems a bit strange to people, but actually it is. And it has to be so, because if you think of it to its logical extent, you'd end up with the whole aircraft being critical if a critical part naturally made the assembly critical. So here we have a definition. Happens to come out of my own procedures, but somebody would have, other companies would have similar definitions, I'm sure, where an installation or an assembly is critical if in a FMECA it's been determined to have a non-redundant, catastrophic or hazardous failure mode resulting from inadvertent disassembly or separation during service, in other words, it comes apart. Misassembly during manufacture or servicing, maybe a non-return valve could go in back to front. Failure to perform a special process correctly, say the bonding of the shaft to the coupling on the tail drive shaft, if that process was done incorrectly. Omission of a component during manufacture or servicing, say an O-ring missing. So you look at the assembly, and if there is a way that that assembly could have a catastrophic failure mode, you make it a critical assembly, and you identify on the drawing critical points where inspectors have to double check with double independent inspection that that critical point has been done right. So let's have a look at some of the design rules for critical parts. Firstly, having identified your critical parts in a list, for each part, you would have a critical parts plan. This is basically a checklist to make sure that everything you're meant to do with the critical part along its entire life through design, production, and into service has been done and was right. Awareness is really important. Every drawing, every technique sheet, everything to do with that critical part is labeled with large, bold letters, 25 millimeters high, that will say critical part or critical assembly. Or in the case where we have a non-critical assembly that contains critical parts, you still want people to be aware. So the boldest label would say this assembly contains critical parts. Awareness is absolutely key all the way through. We would always have separate drawings for critical parts. You would never mix critical and non-critical parts on the drawing. Why? Because you've got to keep that focus on the bits that matter. Drawings would invariably be calling out non-destructive test as appropriate to what sort of part it is for all mechanical parts. The drawings would give a lot of detailed notes on what is required to be done. So, for example, special handling requirements. They'll say this is a critical part. It must be free of blemishes and damage. And we even learned that we had to specify a standard of packaging during work in progress. because what you can't afford is for these parts to receive damage. Caution notes regarding inspection criteria. What exactly is the inspector looking for at each stage of manufacture? And then you would spell out special production rules, things like what we call frozen layouts. This is where the manufacturing layout, the job card, has to be checked by design and approved by design, and then manufacturing can't change it. If anything changes in the process, it's got to go back through the loop again. You have special material control. It's just not good enough to look at the mill certificate and say, yeah, okay, I'm going to put that in store and then use it. When you're receiving material in for critical parts, vital parts, an offcut goes down the mat lab, they turn up a test piece, pull it, and check it really is the right stuff and it was heat treated correctly. Full serialization, I'll explain that later. Production integrity testing, that's where we do cut-ups. So every 50th casting gets cut up to make sure that the process is stable. And we have an enhanced first article inspection process, which I'll talk about. On the analysis, you would always have a verification plan to say, what are we going to do for this part? Well, static analysis, fatigue analysis, floor tolerant analysis, low cycle fatigue test perhaps, high cycle fatigue, whatever's appropriate, it's all laid out in a plan. Independent check stress. When the CVE checks the stress calculations for the part, he would do or she would do an independent check stress just to check that you're getting the same order of magnitude. Reliability requirements, some things we've already heard about actually, double locking on rotating fasteners. Helicopters full of those. Anything on the flying controls, etc., has to have a mechanical double locking. And I'll just click on this hyperlink, which hopefully will come up. And there you see, this is an extract from 25.1309 AMC, again, which just relates to you how for the different categories of failure mode, catastrophic, hazardous, major, minor, we have the different reliability expectations. So you see the 10 to the minus 9 per flying hour under catastrophic, hazardous 10 to the minus 7 to 10 to the minus 9, and so on down to minor, which is below 10 to the minus 3. Let's talk about frozen layouts now, production. With all aerospace manufacture, we always break the job down into tasks in detail so that the manufacturing process is always done the same. The difference with critical parts is the level of detail that you go to. You must have full traceability for every part through every operation, and this extreme detail, as I say, for each operation, you're likely to have a process sheet that tells you precisely how you do it. You don't just say machine to drawing. It tells you exactly what you do, what order, and how you do it with what machine. And then once that layout has been completed, it goes back to engineering where it's approved by design, stress, and the MATLAB, and then it is frozen, and then production cannot change it. So even, for example, if you want to move a turning operation from the Akuma lathe onto another design, you can't do that without approval. And I'll just show you a quick example here. Again, it just gives, this is the front sheet of a critical part job card. All I'm showing you here is the traceability that you're looking for, not just, for example, precursor parts, the castings or forgings, if there were any, concessions that were applied to them, even down to what sort of tooling and measuring devices you use. You want everything to stay exactly the same, so you nail it down. I'm just going to show you here an example of a pretend operation, which I just drew up here, where we're doing a hardness check. Now, on a non-critical part, a hardness check would basically, the operator would say hardness check to Rockwell, whatever number, and give a tolerance, and then the operator would do each one, and at the end he would stamp to say that the whole batch was all right. That's not good enough for critical parts. In critical parts, the drawing will call it up and it'll say, record the results for each serial number on the job card. So here you see I've sort of invented some serial numbers, put the numbers down, and the reason you do that is A, to give exact traceability for every single serial numbered part, but it's a mental interrupt to the operator. When he actually has to write the number down, it's oh, hang on a minute, that wasn't right. And it's an interrupt that helps them to identify. Also, when the inspector is checking the job card, you say, oh, hang on, they're all looking a bit top end, these. Your process is obviously not very well centered. It's that kind of detail that we go to. Full serialization, what does that mean? It means cradle-to-grave traceability. Billets, forgings, and castings, they're all serialized when they're made. And when a billet is issued, the serial number goes on right at the beginning. Every time the serial number is erased by machining, it's put back immediately. Why? Well, the best example I give, funny enough, is not a helicopter crash at all. It was a DC-10 Sioux City Falls. Titanium hub in number 2 engine blew up, took out all the flying controls on the aircraft. They were very lucky to get it down at all. As it was, I think half the people survived. But the titanium hub was found to have had a flaw, which had actually been detected by ultrasonic inspection, but they scrapped the wrong hub. And that's a wonderful example, or terrible example, of why we must serialize critical parts all the way through their life. First article inspection. A normal first article inspection consists of usually the inspector will highlight every dimension on the drawing and highlight every drawing note, and he'll make a list. And then he'll check the tolerances on each of those dimensions. And for the drawing notes, he'll check that those processes or those tasks were actually done. And he'll look for the stamp on the job card and say, yep, that plating operation was done, and he'll be happy with that. For critical parts, we do more. We actually look at those processes and check that they were done correctly. Because if a process has not been done correctly, you want to know at the beginning, not when you get into full series production. And so this is an example of a check that we do, process integrity check sheet. The design office will fill this out, and so depending what the drawing calls up, for example, if it's a metallic part, you'll call up the appropriate NDT, like mag particle inspection for a ferrous part, for example. And if it's heat treated, it'll call up the appropriate heat treatment tick there. You just put a cross there. And what it does, it tells the inspector what he's looking for the first article. So in the case of the mag particle inspection, he's not just looking to see that the operation was done. He will go back and get the level 3 technique sheet. And that will go back to the MATLAB for over-checking. Similarly, heat treatment, you don't just say, yes, this was done according to the spec. You actually say, I want those traces. I want the heat treatment traces that show the oven going up in temperature, holding for the correct time. And then the MATLAB can check the ruling section was right and that the part was actually treated correctly. And so on and so forth through all the different treatments that you might do, surface treatments, castings, hipping, if that's done, etc., etc. It's the level of detail that singles out critical parts. What about procurement? Well, first of all, selecting your critical part suppliers. You can't assign a critical part to anybody. They are always your better suppliers. They're never cheap. They all will need special training, in-depth, flow down of critical part procedures, and a high level of monitoring. So the motto here is keep them close and keep them few, because you're going to put a lot of quality effort into those critical part suppliers. So what you're looking for, this is just a typical sort of list. Accessibility, easy to visit for troubleshooting, good quality system, excellent quality culture, strong technical leadership, and capability in the scope for manufacturing and inspecting their parts. Willingness to conform to your requirements, and good facilities. You want that warm feeling that they are going to be capable to do the job. Now, when you buy critical parts from suppliers, obsolescence planning is absolutely key. I show here a casting. It can easily take a year to qualify a casting. First of all, getting the casting right, because they're notoriously difficult with cold shuts and other problems that you can have. And so after you spent all that effort getting the casting right, developing it with the foundry, and then you go through the qualification process for the part, all the fatigue testing that might be needed, it's an absolute disaster for you if they turn around and say, actually, this aerospace business is too much like hard work and we don't want to make it anymore. So your contract needs to lay down minimum periods of notice of if they want to cease production. So how do we do obsolescence planning? Typically, around about CDR, you would look the risks you'd be looking for is old plant, which is key to the process, supplier, which could get bought out and not want to make the part anymore, material obsolescence, or even legislative process changes, like, for example, CAD plating. We can't use that anymore. And so that's the example of a process which has become obsolescent. So, as I was going to say, at the critical design review stage, you draw up a plan, and then you look at your critical parts, you'd look at them, in typical risk assessment, you look at the impact, and you looked at the probability of obsolescence on each part, and then you give it a risk level, and then you create a plan, which you'd later update in the process. Low-risk items, you'd do nothing, perhaps, until the risk arises. Medium risk, you'd certainly monitor them, probably annual meetings where design, manufacturing, and procurement all get together and look at the key parts and whether any of the risks have changed. But if it's a high-risk part for obsolescence, planning is essential. You might even consider a lifetime buy if it's something which is likely to become unobtainable. Technology transparency, that means specify it with such detail that you could move it if you really have to. And multi-sourcing, again, if you have to. In summary, critical parts are particularly unforgiving of mistakes. Special rules have to be applied for design, production, and procurement, and special levels of monitoring, training, and quality involvement are needed to ensure that personnel at all levels understand the level of care and attention to detail that's required, because it's an order of magnitude greater than you would do for non-critical parts. Okay, thank you very much.